Good morning, everyone. My name is Eli Wilson,
I'm Albert Zuo.
and we're Team 58 from La Cueva High School with the project, a computational model of tree growth to maximize carbon sequestration. So just as an overview of what we're going to talk about today, first we'll go over some related work in the area, then we'll talk about our problem statement and how our work relates to that work. We'll then go over our mathematical model. We represent a tree as a collection of segments, which we use to calculate the process of photosynthesis and generate carbon for growth. We'll then talk about the algorithms we implemented and how we wrote code for this model. We'll go into how we validated the model against characteristics of real tree growth, then into some applications, how we applied it to some situations that could be useful, and then we'll conclude and talk about some future work that can be done in this area. Current work for tree modeling generally follows two different approaches, either rule-based or image-based modeling. Rule-based modeling is modeling trees based on biological rules and focusing on biological accuracy. An example is the work of Carl Nicholas and Sean Hammond. They program allometric rules into the model and focus on studying light competition in a forest. As you can see, their representation of a tree is very simple because they model a tree as being a single root segment or a single stem with a hemispherical canopy over it. The other type of modeling is image-based modeling. This focuses on producing visually appealing trees or copies of real trees, but it is not biologically accurate, and it only models one period in a tree's life, not the whole growth of a tree. So our work is going to differ from that. So our problem statement, our goal was to build a model of tree growth that is, one, based on underlying biological processes. This is important to note that it's different from the previous related work. Previous related work has specifically programmed rules of tree growth into the model, such as allometric rules. Allometric rules are basically finite relationships between different parts of a tree that hold true for all trees. Our goal for this project was, instead of programming those directly in, was to focus on fundamental underlying biological processes and then produce those allometric rules as a result. We want our model to be more detailed than previous rule-based models. As you can see, that model was fairly simple, and we wanted to model at a higher level of detail. We want our model to be computationally efficient, which requires the use of some advanced computing techniques and algorithms in order to achieve efficient simulations. And lastly, we want to validate our model and show that it is valid by showing that, one, as I mentioned, it follows those allometric rules, and additionally, it exhibits other characteristics of growth, such as phototropism and anemotropism. And then if we make a correct model of tree growth, it can be used to apply to situations such as optimizing planting conditions in tree plantations. This is useful. The model is useful because it can determine if and how a tree will grow in a given environment. Now I'll go to Albert, who will talk about our mathematical model.
So here's just a brief overview of how our mathematical model works. So we use light from the sun to calculate photosynthesis, which gives us the amount we can use for growth, which we term our carbon budget. First, we apportion a percentage of our carbon budget towards roots. We don't explicitly model roots, but it's still important to acknowledge that they're there, so we use a percentage. Our model is a general deciduous tree, and so these need to replace their leaves, and so we do that in our model. Next, we use the majority of our carbon budget towards growing in width proportional to the stress it feels, which I'll go into detail later. And finally, it uses the rest towards branching. And that gives us our collective tree. So photosynthesis is what we use to calculate our carbon budget, and photosynthesis is a series of biochemical steps that have three inputs: carbon dioxide, water, and light. Now, carbon dioxide is generally abundant in the atmosphere, and so we don't consider that as a limiting factor. Water is a limiting factor in some areas, such as the desert, but in plantations, their focus is on carbon sequestration, and so they don't really look at water. So we choose to focus on light and competition between trees as our limiting factor. We use the equation on the board there that states that the net biomass accumulation is equal to the total sunlight incident on a unit area, which we can calculate through a double integration, taking into account the sun's position and rotation. We multiply that by the fraction that is absorbed by the tree, and we multiply that by the efficiency of the tree, which takes into account stuff like converting the monosaccharides it initially generates into polysaccharides, such as cellulose, and also the maintenance of the tree, such as cellular respiration. So trees release the hormone auxin when they're under stress, which directly results in the release of cambium, which then results in tissue growth. So we propose that trees grow in proportion to the stress they feel. At the segment level, we calculate the gravity and the wind forces. The wind force is a little more complicated, so I'll go into detail there. The wind force is equal to 0.5 times the drag coefficient times the air density times the area of the leaf times the speed squared. And we plug these forces into the stress equation that came from Machinery Handbook, and we sum these two stresses to get our total stress, and we take a proportion of that and add it to our width each year. After we use the majority towards growing in width, we then look at branching. The chance of branching is proportional to the light available at the target location, and this makes sense because trees want a return on their investment. They don't want to invest in an area and then get nothing back. So this leads us to the death of branches, which is when trees use more than they return from the photosynthesis, we prune them. So here's just a video of our simulation running, and we'll talk a little bit about it.
So this is our simulation running in real time. This has smaller leaves to show that, that wood growth. As you can see, some of the branches are dying off, as Albert said, because they're using more carbon than they produce. Also, if you look on the ground, as we change to another tree, you'll see that there are 5 different shadows on the ground. This is because each tick in our simulation is 1 year, and we approximate light to travel in 5 different directions. So taking into account the sun's position in the sky over an entire year, that's what creates those 5 shadows. Based on that light, this is one with varying light conditions, so it's with a majority of light coming from a different angle. This shows the characteristic of phototropism, which is the tendency of trees to grow into the light, which you'll see from about this angle here, that tree's tilted towards that light.
That's gorgeous. That's really great.
Thank you. This is an example of a tree where the environmental parameters are too much for the tree to handle. This tree is subject to 75 miles of wind, 75 miles per hour of wind, and that's why it died off and it just couldn't handle the stresses that it was subject to. Lastly, this is a forest or a plantation with 9 trees growing in a 10 by 10 meter plot. It's important to note that the trees will grow upwards, and they're really shooting upwards in comparison to the previous trees, and that's because they're competing for that light, and they're trying to get up as high as possible. It's important to note that all these characteristics I've talked about, we didn't specifically program into the model, but due to the accuracy of our biological model or our mathematical model itself, it's still shown. So to write code for this, we wrote code in Java through the Eclipse environment. Visualization was in OpenGL graphics library. And a rough outline of our simulation is that a simulation is created with certain parameters, such as the size of the simulation, wind, speed, gravity, light conditions, etc. And inside that simulation, we create a tree or a group of trees. A tree starts out as a single root segment, and based on the mathematical model that Albert described, that root segment will grow upward and branch outward into a tree, which is collectively a group of segments. A typical tree has about 9,000 segments and 2,500 clouds of leaves, which is obviously a lot of computing to be doing if you think about how we're calculating the stress for every single segment. And so it requires some advanced computing techniques to do that efficiently. We're going to talk about a few technical challenges that we ran into when coding for this. The first one is edge effects on the 10 by 10 meter plot. We didn't want when a branch or a leaf approached the side of our world or our simulation for there to be any weird effects because it doesn't have space to grow into, or there are weird light conditions. So what we did is we implemented a wraparound world using modular arithmetic. As you can see in the picture, when a branch goes off one side of the world, it will come in on the other side. This essentially allows us to model a small plot within an infinite forest, which is very useful in the applications we'll talk about later. The next technical challenge was graphics and efficient tree processing. As I said, we use the OpenGL graphics library, which allows using matrix transformations to have some very powerful graphics output. Additionally, we used multi-threading, which goes hand in hand with efficient tree processing. Multi-threading is a type of parallel processing in which different cores in the computer handle different parts of the program. So in our program, one core of the computer handles updating the tree, while another core of the computer handles drawing the tree with the graphics. This greatly increases our computing, or helps our computing time. Additionally, we use recursion with caching. Recursion is a technique used to split up a large problem into a series of smaller, less complex problems, but similar problems. Basically, a tree is a naturally recursive data structure because you can think of a tree as a bunch of smaller trees where each branch is its own tree. And if you continue doing that, you can eventually reach your base case or your simplest case where your, quote, tree is a single segment. And in the code or in the computing, the computer will then cycle back through the stack and end up updating or calculating some value for the entire tree, which is what allows us to do that efficiently. Additionally, we used caching, which is basically storing the value of variables that we calculate until they have to be recalculated. We found that a lot of times in our code, we were calculating a certain thing multiple times when it didn't have to be recalculated. So when we implemented this, our code ended up being up to 4 times as fast, which you can see in this video here. On the left in this simulation is a forest running with multi-threading and caching, whereas on the right, there is no multi-threading or no caching. And as you can see, as it gets to be large, the one on the left is much faster. And we won't let this video run for the whole time, but in fact, we'll let it go for a little bit to just see how big of a difference it is. But the one on the left is about 4 times as fast as the one on the right is still running.
Did they achieve the same results?
Yes. Actually, the one on the, since they're a different version of the model and there's a slightly random chance in growing, they're not going to be the exact same results, but yes, essentially the two produce the same.
I thought these trees were deciduous.
They are deciduous.
I didn't see them without leaves.
Oh, well, each tick in our program is 1 year, so we don't draw them when they don't have the leaves, but as Albert said in the mathematical model, we take into account that each year they lose their leaves, and then they're going to have to replace them the next season.
And that's also considered in our total sunlight incident on a unit area, which only considers the amount of light and not like the night times and stuff like that.
You're not showing branches that fell off.
Yes, once a branch is considered dead, then it's gone.
So the branches aren't accumulating on the ground.
Do branches cross or connect or?
He'll actually talk about that right now.
So 2 more technical challenges we faced were light propagation and collision detection, which we solved through the use of a voxel grid. So here you can think of a voxel grid as a 3D index of space, where each voxel, or one of those little cube things, is a pixel of volume. So this allows us, in terms of light propagation, that gives us our shadow. We have to calculate this light throughout the tree, where some parts are shaded out compared to the others. And so this allows us to compute efficiently and also accurately the light values. Also for collision detection, like you talked about, we ran into the problems with different branches hitting each other, which we'll see here. And what happened here is a lot of the branches branched into the same space, and that gave this really bushy tree. And so this is actually one of our first iterations of the model, and now we'll go through a short progression of our tree. Each time we added something new, and you can see the tree gradually progress to where we are now.
And we're going to go through this fairly quickly right now. Feel free to later, if you have any questions, we can go back and answer anything.
So now that we have a model, we want to validate it against those allometric rules, as Eli talked about, which were proportions or relationships between trees. So first, this allometric rule states that the mass of the leaves is equal to some constant times the mass of the stem to another constant, which you can see on the screen. And so what we did was, in 30 trees, we took the actual mass of the leaves, and we compared it to the predicted mass of the leaves using the mass of the stem. And if our model matched this allometric rule, then that ratio should be about 1. And you can see that there is some variance due to the random chance that Eli talked about earlier, but our mean was 0.955, which is really close to 1, justifying this allometric rule.
I'm not familiar with this word,
It's it's a term for relationships between parts. It's also used in a lot of like animal stuff, where it's like relationships between maybe like their feet or something, but in terms of a tree.
There's no biology here. It's just
It's kind of describing what the shape of trees should be. So all trees tend to follow this relationship, that the mass of the leaves and the mass of the stem have this certain relationship with each other. And so it's just that's just observed. There's no right. It's empirical for all trees, and
but
it's observed in nature.
Yes. So next we looked at these two. The one on the left states that the height is proportional to the diameter to the 2/3, and the one on the right states that in younger trees, the mass of the leaves is proportional to the total mass, but in older trees, the mass of the leaves is proportional to the total mass of the 0.75. And using an exponential transformation, this should give us a roughly linear relationship. And you can see in the graphs that after the first 10 years, when our tree has not reached reproductive maturity yet, that it is roughly linear afterwards. So next we looked at some emergent properties of growth. One is phototropism. In positive phototropism, which trees exhibit, trees will grow towards the light. So we used a hypothesis test. First, we looked at the majority of light coming straight down to make sure our tree didn't have a bias towards growing one particular side, and we found that it didn't. Then we changed it so that the majority of light was coming in from a specific direction, and we found that our tree did in fact exhibit phototropism. And here's just a visual representation. The tree on the left, you can see, had the majority of light coming straight down, which made that shadow. And you can see that the tree mostly grows straight up, whereas the tree on the right, the majority of light is coming in from this direction, and that gives us this shadow. And you can see that the tree is branched towards that way.
But the validation here is just that it looks right. There's no...
The hypothesis, so what we did for this was we looked at the center of mass for 60 years in a tree's life and found, because our tree starts off at a base coordinate, and we found if the center of mass was tilted towards one particular side, and using a hypothesis test, which is a standard statistical test, we found that our tree did in fact tilt towards the light. So
what is the hypothesis?
So the null hypothesis states that the center of mass has not changed and is 5, whereas this one states that it is greater than 5, since that was the direction we had it coming from. If you want, you can see some of the tables of our data that we took, and that might help a little.
Thank you. Okay.
So next we looked at allometropism, which is how trees respond to wind conditions. In higher wind conditions, trees should grow short in height but wider in diameter to deal with the extra stress. And so again, we used a hypothesis test, and we have the tables for that too. And we found that in fact it does exhibit. So here's just a visual representation. The tree on the left experienced lower wind speeds, and so you can see it's a lot taller, but also less wide compared to the tree on the right. And now Eli will talk about some of our applications.
So after we've validated our model and showed that it exhibits a lot of characteristics that real trees show, we decided to apply it to tree plantations. So in tree plantations, trees are grown to either sequester carbon or produce timber or things like that. And we came up with the idea that we could use our model to quickly determine the optimal planting conditions to plant these trees in. So for this experiment, we tried to vary the spacing between trees to optimize the amount of carbon that was taken in by a 10 by 10 meter plot. So we ran 14 different spacings 10 different times, and we measured the total carbon uptake of the plot after 60 years by measuring the total mass of all the trees after that time. And we found that for our general deciduous tree that we model, that distance is 1.67 meters, which if you look at the graph, it may seem slightly insignificant right now, but if you extend that 10 by 10 meter plot difference to a square mile of plantation, it's 1.3 million kilograms of carbon of a difference. Another application we did is maximizing timber production, which is basically the same experiment that I just talked about, except the only difference is that we only measured the amount of wood that had a diameter of greater than 15 centimeters, or that was usable for timber. And it's interesting to note that the optimal spacing was actually different in this case than the carbon sequestration. It was 1.43 meters in this case. And both these applications just demonstrate how our model can be used to determine these conditions really quickly for experiments that would otherwise take upwards of 20 years, because you would have to plant the trees, wait for them to grow, and then measure these values. And also the values are extremely difficult to measure. So our model has a lot of potential in that area for a specific tree, which Albert will go into.
So the specific tree we looked at was the sugar maple, which is often used in timber and syrup production. And so we looked at the heights and we matched the average growth rates. We set the cutoff date at 40 years because that's a pretty reasonable time for trees to grow in a plantation before they cut them down and harvest the trees.
So to tie our model back to the related work that we talked about before we conclude, we just want to really quickly talk about, on the left, you'll see the rule-based model, which is the previous rule-based. And as you can see there, this is very simple, but it's biologically accurate, and it follows those allometric rules. On the right is an image-based model, which is focusing on producing a copy of a real tree, and it's very detailed, has a detailed shadow, etc. And we feel that our model kind of combines the best of these two approaches and bridges the gap between these two, because we have the level of detail of an image-based model, but also the biological accuracy and the allometric rules of a rule-based model. In conclusion, we feel that we created and implemented a biologically accurate model, and as I said, it kind of bridges that gap. We also made use of a few advanced algorithms that enabled efficient simulation. Our model would have basically been impossible to do without these algorithms such as the voxel grid and the recursion. We also validated the model by showing, one, that it generates these empirical allometric rules that all trees follow, and it does so from underlying biological processes rather than programming them in. We also demonstrated that it demonstrates other key characteristics of growth, such as phototropism and anemotropism. And then lastly, we were able to apply our model and demonstrate the application of our model in tree plantations.
So some future work we would like to do is extending our model to different types of trees. Specifically, coniferous trees would be nice to model. Adding water as a limiting factor would make it more accurate in areas that aren't plantations where water is a limiting factor. Adding reproduction would make modeling forests for hundreds of years where reproduction starts to take a factor more accurate. And finally, we'll be presenting this work at the Botanical Society of America conference, where we will be presenting an oral paper and poster.
Just really quickly to talk about the teamwork. We basically worked together on everything. It took a lot of time. In general, as kind of we showed when we presented, Albert worked a little bit more on the mathematical model. He understood more of the three-dimensional trigonometry that was involved with calculating forces and things like that than I did. But I have a little bit of a longer time coding, so I worked a little bit more on the programming. But in general, everything was worked on together. Everything was done through pair programming, etc. We'd like to thank our sponsor, Mr. DeWitt from La Cueva High School, as well as our consultants, Dr. Hammond and Professor Hansen from UNM. These three all helped us a lot from the biology side of things. Sean Hammond actually works in tree modeling, as we used his for some related work. And they were very helpful in advising us on the biology side of things, as well as my dad, Randy Wilson, who helped us figure out the graphics with OpenGL. And whenever we had bugs, he was helpful if we absolutely couldn't find it to find it for us. We'll now take any questions, anything else that you guys have. Sure.
You spoke about the difference in growth between young trees and old trees, sort of a 10-year boundary, and you talked about reproductive maturity. Is there anything in your model that makes young trees grow different from old trees?
So we don't actually have anything that grows different, which again, I think kind of validates our model and showing that even though we didn't explicitly program stuff like between young trees and old trees, it still exhibited these rules throughout its life.
There's one thing that might be a slight difference. The only thing that I can think of is that I believe actually we took this out of the code, but for some time we had in young trees the branch angle factor, or the amount that it deviated from the center, was reduced so that it grew straight up for the first few years. And it would have grown straight up regardless, but sometimes it would kind of have these weird branches at the start, and that exhibits kind of gravitropism, which is trees growing upwards.
One of the expo judges is Ed Angel, a professor from UNM who's written a textbook on OpenGL.
Okay.
He should see this.
Yeah.
Has he seen it? Do you know?
I don't think so, but I mean, it was very useful. Originally, we wrote this in processing and making the transition. We wanted it to be, wanted it to be efficient and things like that, and OpenGL was really useful.
Yeah, we got to get Ed to see this somehow.
Steve, and your discussion of water as a variable, so is water constant even in each segment, or does it change as a distance from the roots?
Sorry, what was that? Water? Did you say water?
Yeah, water. Yeah, water. Like water per segment. Is it constant throughout the tree?
I believe, well, in our model, we don't model water, but I believe that in areas with higher diameters, there should be more water, and so I feel like that number would increase, like down the tree you go as the stem gets wider.
But basically for our model, we assume that water is abundant and the tree has enough water. That is something that we would have to take into account once if we did start modeling that.
And what about interactions between segments? So, I mean, does stress somehow propagate through the tree? Are there stresses a variable per segment?
That's a good question. So yes, each segment has a certain amount of stress that it's subject on, and you can think of it as there are more segments above a certain segment. Those segments are going to weigh more, and so they're going to have more force due to gravity, and that's going to exhibit more stress on that segment. So yes, there is a relationship, but they don't necessarily communicate with each other. They only calculate forces locally.
And that's also another reason why we wanted to look at this. Trees don't have a long-distance signaling system, otherwise known as an endocrine system. And so those allometric rules, many of those researchers just assumed them to be, and we wanted to propose a possible explanation for why they grew that way.
Is that true for aspens? I think the aspen tree isn't all common somehow.
Sorry?
An aspen tree is both deciduous and the root system connects all the trees. So I don't know if that means.
That's interesting.
Yeah, that would be something we would look into.
Did you see any unexpected results in your model? Or something that came up that you weren't expecting?
There weren't bugs.
There weren't bugs, yeah.
Well, I mean, actually, to be honest, we were quite surprised and really excited about things like the phototropism and anemotropism, because when we started the project, we didn't expect for those to happen. And then it kind of came up as a slight suggestion of, hey, you could check this. And then we checked it and it worked great. So those were things that we really didn't expect or intend, but they ended up working out due to that biological accuracy.
So one thing that actually does fit your description was, if you remember this picture here, you can see it clearly doesn't look like a tree. And this is the first time we added stress. Growing in with proportion to stress, and so here our stress proportion was really large, and so it grew a lot each time it felt the stress. So after we adjusted it, that gave us this, and it looks a lot better.
This is one of the exciting things about computer modeling, is when they start doing things you don't expect them to, and when they do things you can't explain.
Yeah, we were really excited about those things.
Or when they do things that you didn't expect the model to do that actually happen in reality.
Right. Exactly.
So you've done a generic tree. Have you looked to see how accurate it is with different species of trees?
The only one that we've worked on with that, as Albert talked about, was the sugar maple, which we'll go to. And all we were able, it's kind of hard to get specific statistics for growth of, say, sugar maple, because no one goes out and every year measures the height of a sugar maple. Oh, really? Well,
we need to do a better literature search.
Okay. We had a hard time finding that, at least for sugar maple. But the idea is that with the parameters that we have for growth, if we can change those to different trees, it should be relatively easy to then model a specific tree. But since the allometric rules that we model are supposed to be true for all trees, then the model itself should remain relatively intact.
You believe that? You think it's true for all trees?
Yeah, well, I mean, that's what we found in literature, is that allometric rules are true for all trees.
And especially in discussing.
And that's
Go ahead.
accepted
Yeah.
by
Yes.
the community.
Allometric rules are what biologists
They usually
thought
look
when
for
they were
animals.
measuring trees, and they
Right.
didn't really understand the underlying biology and how it happened. So they'd measure the height of the trees.
I
and
understand that, but
Oh.
that's not really my question.
Oh, okay.
She was wondering if it's validated,
Okay, yeah.
right?
As far as we know, we believe that in everything that we've found, that yes, it is validated and generally.
I mean, speed of light's a constant, right? Unless it goes through
Yeah,
glass
and
or
then
water or something.
and in discussion
Makes-
with a lot of the
A lot of simplifying rules if you do
Yeah.
it this way.
Yeah.
Okay.
Yeah, and then in discussion with Sean Hammond and Professor Hansen, we found that in fact these do exhibit, and they gave us a lot of literature to look at, and throughout that literature we found that, okay, these are allometric rules and they are pretty empirical.
Why don't you say what's behind your question?
I think you need to look at the bigger picture. I think this is fine for maybe a farm, but how realistic, could you extrapolate this to trees growing any place? And I think that would be very difficult because you can't ignore water. You can't have photosynthesis on leaves. If you don't have leaves, you need the water for the leaves. So I think it's great for farms.
That's sort of on their list of, future work.
No, it's a really great, it's a great start. No, it's a really great start.
Context, starting out in the 70s with fractal dynamics sorts of things, the Japanese were using this and developing these same sorts of things. Now, this is an advance from what I saw back then, but, they were using it for designing gardens in Japan with various trees, and there are different allometric rules for branching, and that these guys have been using for ginkgos versus pines, and they've worked. So you can find papers on that, on how to design your garden, and how's that tree grow, and should I put it here versus over here. Now I'd be real interested in you guys thinking about in the future, if you keep doing this, of how would trees grow in an urban environment where you have various strange wind stresses, and instead of going out and looking at how we develop a plantation, what would this look like on a high rise or something like that. There's been a lot of interest in how do we bring carbon sequestration close to home.
Yeah.
So you could look at some complex systems that way. That'd be really neat.
Okay, we're out of time. Thank you.
Thank you.
Nice tires, guys.